Okay, this is David Zierler, Director of the Caltech Heritage Project. It's Wednesday, March 9th, 2022. I am delighted to be back with Dr. Lee Hood. Lee, it's great to be with you again.
Pleasure to be with you.
Lee, today I'd like to start with the few open threads that we left in the 1990s. One, just a fun question, working with Dan Kevles on the Code of Codes. Looking back, in what ways has that book aged well about the goals of the Human Genome Project? And in what ways might the book need a second edition or an update?
Well, I think the book could certainly use an update because so many things have happened we couldn't conceivably imagine. But on the other hand, I think from a historical point of view, it is a fascinating book because the various chapters are lectures leaders in this area gave at Caltech that Dan and I then, in some cases, edited rather heavily, but they did represent the thoughts, the ideas, the vision of the people that had them. And I think in that sense, some people had small visions and some people had big visions, and there were maybe one or two that didn't have any vision at all, one could tell. But I think it was a very fair historical representation of where we stood in roughly 1990 or so.
Yeah.
I will say that the chapter I wrote there really did presage systems biology and some of the things that later came to be dominant themes in my life. And I'll tell you, it was an exceptional experience writing a book with Dan Kevles, who, of course, it was an accomplished author, well-published, and he became, in the course of that, a good friend. And I hated to see him go off to Yale, but he was a wonderful person to co-edit a book with.
Lee, thinking about Dan Kevles, I'm curious if you were following closely the so-called Baltimore Case and that whole brouhaha in Washington with John Dingell.
I did. I think most of us in molecular biology followed it quite closely.
What were some of the takeaways from you as you were watching this unfold?
You know, I think the biggest takeaways were total transparency and making sure people understood what each was trying to say or what each was trying to ask. I think the book that Dan Kevles did on that is really the classic. I think he nailed it in most of its major dimensions. And I think it was a sobering experience of how time-consuming and encompassing an issue like that can become if it gets away from you. Yeah. And I think it did get away from David Baltimore.
Since its development in the 1990s, looking back, what has been the impact of the DNA Inkjet Printer technology, albeit on genomics, biology, and medicine? What do you see as its long-term import?
Well, I think its long-term importance is it was a technique that, was developed in my lab, and then Alan Blanchard, who developed it, then went with a company I spun off with Lee Hartwell and Stephen Friend called Rosetta. And at Rosetta, he finished the last stages of development But Rosetta was then purchased by um, Merck, and for its computational strategies and techniques and so forth. But Merck decided they didn't want to get into that business and quickly sold it off. And in the process of selling it off, the inkjet technology went to Agilent, one of the major instrumentation companies in the field of biology. And they've used it since that time in large scale synthesis, both of DNA arrays and very large scale synthesis of a multiplicity of DNA fragments and so forth. So I think it provided the fuel for essentially allowing nucleic acid fragments to become reagents in biology, and the arrays to give us a quick and dirty assessment of complicated gene expression patterns in cells, in tissues, even in whole organisms and so forth. So I think it was really the next stage up from the automated DNA synthesizer, which, synthesized one fragment of DNA at a time or a few later on, to where you could do, there wasn't really any limit. You could get up into hundreds of thousands, millions if you wished.
Lee, turning toward the turn of the century, what role did the internet itself have, the so-called dot-com revolution? What role did that play in making your vision of systems biology viable at that point in time?
Well, I think the major role it played was it enabled science to instantaneously spread any new findings across the world. It allowed you to access easily the very best science in the world, and if you wished, come to know those people. Thomas Friedman wrote a book called I believe it was the world is flat, or the earth is flat.
The world is flat, I remember.
Where he made this point that it basically democratized education and business and a whole variety of other things. And it democratized science. It made collaborations much easier. It made knowledge instantaneously accessible. It was one of the accelerants that propelled the world of science forward in really exciting ways.
And I wonder, particularly a value for systems biology in your emphasis on a multidisciplinary approach, if the internet simply provided more access where biologists could get out of their academic bubble and see what was going on in related disciplines.
Well, in theory, that's true. In practice, biologists don't tend to get out of their bubble very easily. I can tell you that. But what it did make possible was for young people to learn multiple disciplines and easily fuse multiple bubbles. So they went out into the world with integrated cross-disciplinary talents.
Lee, when it was time to move on from the University of Washington, what considerations were there about retaining some academic affiliations or privileges with the campus?
Well, I'll tell you, my leaving the university was rather abrupt, driven by fundamental disagreements with the dean of the medical school. And I was so annoyed at how I was treated is the last thing in the world I thought I wanted to retain were connections with the medical school. And frankly, I didn't. But I did value connections with one, bioengineering. They had marvelously trained students, cross-disciplinary in nature. Number two, with immunology, which after all was a field I had up until relatively recently continued to pursue. And then number three, with computer science, which was a field into which I'm going. So I had adjunct professor appointments in those three departments, and they enabled me to get wonderful graduate students and to have interactions with the faculty and all. So I never felt at loss for a lack of academic connections apart from medicine, which the relationship with the dean made it very, very hard to set up collaborations and carry them out. So I didn't bother.
Lee, more broadly, in the early 2000s, what was happening at that point that made you think that the development of P4 was a viable approach? What was going on? Was it computational power? Was there the public clamoring for improvements in healthcare, developments in biotechnology? What was it at that point?
Well, at the earliest point, it was really a conceptual vision of medicine, okay? And basically, it was thinking about medicine or about healthcare and asking the question, what are the ideal features for medicine or healthcare? And I decided, we started with 3 Ps initially: prediction, prevention, and personalization. And those 3 Ps are really all about the science, okay? The 4th P that it came a little later, participatory, is a P that is one, the most difficult of the 4 to achieve, and 2, it's a P that really relates to psychology, sociology, economics, and a variety of other kinds of things. So it was a terribly complicated kind of P, but a really central P, because if we're to revolutionize healthcare, as I'm proposing, we have to persuade patients, we have to persuade physicians, we have to persuade healthcare leaders for the healthcare systems, we have to persuade the regulators, we have to persuade the other members of the healthcare community, pharma, technology companies, diagnostic companies, data generation companies, et cetera, et cetera. So the question of, and with the science, we really have established the validity of what I call precision population health through Airavail and its 5,000 patients. That is, we've demonstrated prediction and prevention and personalization, and we've really pushed to a very clear picture of the science of wellness and the science of prevention. So what was clear that I had to do after Airavail failed was set in place a very large-scale project, a 1 million-person project, and have it be a demonstration over a period of 10 years of how effectively the science of wellness and prevention works, that we could improve the quality of healthcare and prove it quantitatively to payers so they'd be willing to pay for it, that we could demonstrate unequivocally that we could manage the aging population, and in fact set up a means so you could slow, if not reverse, the aging process. And I think we've taken a big step toward that. And we needed to be able to deal with the explosion of chronic diseases. And we were able to demonstrate beautifully in Airvale that we had 167 transitions from wellness to disease, most of the chronic diseases we know about. And we looked at 10 that transitioned to cancer. And for each of them, in blood draws drawn prior to the diagnosis, we were able to show there were blood analytes that were off scale, off the norms for the population that existed then. So we had, for example, protein biomarkers that not only said something was awry, but in a number of cases could predict what the disease to come was. And this, in some cases, was 4 or 5 years before clinical diagnosis. And from that emerged the idea we can get biomarkers for the earliest disease transitions, and through collaborations with academics and pharma, we'll be able to reverse those transitions before they ever become a disease. And that led me in a compelling way to argue it really was time for a 1 million person project. And, you know, initially I thought I could get it funded via industry, but it clearly became certain that the funding should be just as the first human genome project was from the federal government. And in fact, we ended up calling this project the Beyond the Human Genome Project. And the beyond part was the longitudinal phenome, which gave us 70% of the information for making people well, preventing disease, and when it happened, dealing with disease itself. So so I would say Airvale in the earlier 100-person project we did in 2014 kind of validated this idea of precision population health along the lines that I've talked about here. Airvale lasted from 2015 to 2019. And it was after that I said, we'll do a 1 million person project and we'll correct the mistakes that Airvale made and we'll move on and transform healthcare. And of course, the big visionary idea of Beyond the Human Genome Project is that we're going to create the infrastructure that will make it possible to assess and optimize the health trajectory of each individual for body and for mind, for brain. Okay, that's the essence of what we wanted to do. And we had all the tools to do it. And it was necessary to put forth an organization, Phenome Health, which was created just this past year, that will drive this whole process and will accrue the critical partners we need to execute and the partners we need to help us with technology, with computational tools, with clinical sophistications and the like. And we've done that. We stand, I think, in a very good position as over the past 6 months, we've begun to lobby the government for this second genome project.
Lee, as you well know, for people in the United States who agitate for a better model in healthcare, they often look to other countries, Japan, Scandinavia. When you were putting together the P4 vision, was there a playbook anywhere else in the world that you could look to as a useful model for what you wanted to do here in the U.S.?
Absolutely not.
Simply didn't exist.
I mean, what I will say is in the last few years, 4 or 5 years, there have been some major 500,000 and 1 million person projects. each of which have done very small parts of what we propose to do with Beyond the Human Genome Project. NIH a few years ago started a million-person project called All of Us. And it's basically a research project, and they are generating just a small fraction of the data we feel is really necessary, but they're using that data to do clinical studies in various ways. And the British Biobank is perhaps the most successful. It's a 500,000-person project that has done detailed genome analyses and is just barely now starting to do some phenomic analyses, but very interesting things have come from that. But Beyond the Human Genome Project takes it an order of magnitude further. It's interested in health for the mind as well as for the body. None of the projects even think about the mind. It's interested in getting multi-omic data, phenomic data, and integrating with genome data, with electronic health record data, with outcomes data, with brain data, with and microbiome data, et cetera, et cetera. And so we'll be integrating data on an incredibly large scale, and each different type of data that gets integrated with the other gives new insights into human biology, disease, and generates actionable possibilities that will drive the process of wellness and disease prevention.
Lee, with your election into the National Academy of Engineering in 2007, which made the so-called Triple Crown membership, the National Academy of Sciences, the National Academy of Medicine, up until that point, did you ever think about yourself as an engineer? Did you ever think about, for example, the automated DNA sequencer really as a feat of engineering, as something you accomplished?
You know, I did, and that was partly due to my father, who back when I was in high school, as I think we discussed, ran these, he was an electrical engineer, and he ran a whole series of courses in the summer that he had me take with his men. So I got an exposure to engineering while a high school student, and it really changed how I thought about biology with circuits and all of these kind of things. And so, yes, when I started doing the engineering at Caltech, and that was the issue, that one of the issues of discontent from the senior faculty in biology. They didn't like engineering in biology, and they wanted to move me to engineering. And so yeah, I thought of myself as an engineer, but you know, I never in a million years thought I would end up in all three national academies.
Amazing.
So I mean, that was it's an unexpected bonus coming from the fact I was willing to embark on new careers at various stages of the evolution of my career.
As Bill Dreyer says, always at the cutting edge, right?
Always at the cutting edge, right.
Lee, we talked already about the origins of ISB. One interesting point, how did the country of Luxembourg become a partner with ISB?
Well, you know, ISB, when I founded it in 2000, had no endowment, had no major supporter of any kind. We essentially ran on money that we received from NIH for doing research, plus a little bit of philanthropy. And I was always desperate to figure out how we could have a little more leeway and financial flexibility. So I would guess in 2005 or so, I came up with the idea maybe I could find a country that would be interested in building a systems medicine institute, and ISB could help do that, and in doing so could get some funding. And the first possibility that came up was Israel. I met an Israeli fundraiser at a party of some sort or other and was talking about my vision of systems biology. And he said, this sounds like something that Israel would really like. And I said, well, they'd be a terrific place to get systems biology instituted. And to make a long story short, I spent a number of weeks in Israel visiting all 7 major academic institutions, including the Weizmann Institution, which would have been the logical home for this, trying to persuade them that this was a good thing to do. And the only bite I had was one in southern Israel, where the college president saw that as a way to make his small southern university a player in big time science. So he approached me and said, look, we'll go together to this fundraiser and we'll raise $100,000 to build a building and set up the systems medicine, and then we'll raise 100 million. I'm sorry, it was 100 million for ISB. And I said, gee, that sounds absolutely terrific. So he had plans drawn up. We collaborated on how we could do it, how we would set it up. We persuaded a number of Israeli scientists that they would participate in this process. And then suddenly one day, the American Israeli fundraiser sent me a telegram when I was actually over in Israel and said, gee, I'm sorry to report I'll have no problem raising the money for the systems biology building and program, but I won't be able to raise the money for ISB. And, you know, I put an enormous investment in my own money and especially my own time. So it was a devastating blow. But I went back and reported that. I will say the chair of my board at that time was Roger Perlmutter, who was a good friend, a former student, and he was very skeptical that I'd ever raise any money from a country. And he said, well, I hope this has cured you. And I said, no, I just didn't find the right combination. So, and I did try then 3 other combinations. Calgary was enormously oil rich, and the Hereditary Foundation had an enormous amount of money for building science in Calgary. So I got invited to come and make this kind of proposal. And let me just say, I went through about a year of flirtation, and with Calgary, I came to the conviction that they had a lot of money, they had big eyes, and they were utterly incapable of making any kind of decision whatsoever. So I just said, you know, after a year of flirtation, I said, don't have any more time to waste on this. And then an old friend of mine from NSF, Bill Harris, sent a telegram to me and said he'd taken over in Ireland the equivalent of the National Science Foundation, where he worked when I knew him. And he was really a successful administrator. And he said, I want you to bring systems biology to Ireland. So again, I spent another year. I went to the 4 major centers in Ireland and gave them all the pitch. And what Bill had proposed, and all four agreed to initially, was that they would put out an RFA and that each of the four colleges would compete for it. And I would help each of them write their proposals. And then we'd get an international committee to judge the best, and we'd get a Systems Biology Institute started. So, and just before the RFA was to go out, arguably the best university in Ireland, Trinity, wrote Bill and said, we've decided we don't need Dr. Hood or ISB. We'll just do the systems biology ourselves and leave him out. And so Bill called me up in a dither and said, look, what are you going to do? And I said, it's not a part of the agreement. I'm dropping out. Because it's conceivable Trinity could have written the best proposal. And again, all this work and effort I put in would or not. If they want it, nothing happened. So I said, I just can't justify it. And it turned out that Bill had been offered another job back in the US and had become disillusioned with some of these kinds of politics. So anyway, that was, and then my last failure, which was a unique failure, was Korea. I had a good friend there who was really excited about systems biology. We set up something, the government was going to fund it. It was all ready to go. And without going into any detail, there was an election. A new party got in and they canceled all the major programs of the old party. And boom, it was over. Just again, it had taken roughly a year. So the final thing was I had done some consulting for PricewaterhouseCoopers, and they'd followed my ordeals. And they said, look, we really think there is a unique opportunity with Luxembourg. They've asked us to help bring them up to snuff in science and especially in biology. And this is an opportunity to do so. So I went and told Roger again for the fifth time I was going to try. And he said, Lee, you've wasted so much time. Don't you ever learn? This isn't going to work. And I said, well, I'm going to try it one more time. And he said, do you believe in the tooth fairy? And I said, what do you mean? He said, I don't believe in the tooth fairy, and it's going to take the tooth fairy to get $100 million for Luxembourg for you. And I said, well, I'm going to try. I am very stubborn. So we had a concerted effort with PricewaterhouseCoopers, really helping pave the way in lots of different ways. But in sum, what we finally agreed to do is, one, set up a center for systems biomedicine that would be appended on to the biology, a newly minted university at Luxembourg, I think 3 years old at that time, had. Their biology was utterly classic and descriptive. So the Center for Systems Biomedicine, and we agreed, we would recruit a good director, which we did. I can go into as much detail as you want. And B, that we would set up a research network to serve as interactive collaborators for this newly minted institute. We'd help recruit faculty members. We agreed to take on the training of 12 postdoctoral fellows from Luxembourg in all the different disciplines of systems biology. And they signed an agreement that they'd go back to Luxembourg for at least 2, if not 3 years, and transfer that knowledge and so forth. In return, they agreed to give us over, this was a 5-year period, $100 million. And the focus was A, to help them do all these things, but B, P4 medicine and the technologies and computational tools you'd need to do it. And that was the funding that A, made it possible to recruit Nathan Price, who played a key role in the wellness programs that I've talked about. And B, it drove faculty at ISB and in this distributed network to make some really striking inventions and improvements and so forth. It was an overwhelming success. So anyway, I did succeed in bringing in that $100 million from Luxembourg. What drove the whole thing and made it possible, and it was solely due to him, was the Minister of Economy, who was convinced this was necessary to really drive the development of biotechnology industry in Luxembourg. And we introduced them to lots of people and helped them in a lot of ways. But he was the one that absolutely forced this through for that 5-year period. I'd hoped to be able to do a renewal and continue with that, but he left to go into a major consulting job. And when he left, then everybody in Luxembourg said, well, gee, why are we giving this money to ISP? Now that we're all set up, we can do it all ourselves. So that was the end of that. But it was a great, successful idea.
Lee, shortly after, tell me about the origins of your partnership with the Wexner Medical Center at OSU. How did that come apart to create P4MI?
Well, the P4MI actually was created just out of ISB. It wasn't, there were no other major collaborators. And the idea was that after Airavail had failed, maybe we could have a small institute run by a physician that did many of the things that Airavail did, so we could have a watered down form of scientific wellness and so forth. And that actually was an idea that was good, but we didn't have the personnel to make it a success from a business point of view or from a scientific point of view. And having a kind of 3 or 4 person P4MI Institute just was not a good idea. It's you need a much bigger infrastructure to do something that's really going to be meaningful. And of course, that's what'll come out of this 1,000,000-person project that we're starting to set up now. And we're actually thinking about creating Airavail 2.0 and then bringing it to some of our partner industries to have them benefit their own staff and at the same time work with optimizing scientific wellness and healthy aging and so forth. So anyway, that was an unsuccessful endeavor that was complicated and expensive to unwind, I will admit. So,
Lee, when you won the 2011 National Medal of Science, did you get an opportunity to interact substantively with President Obama at all?
Well, he spent, I would say, 5 minutes with each family, and we had a chance to talk with him on a one-on-one basis. And he gave an absolutely terrific speech to the conference. So I felt I got to see who he was and what an exceptional individual he was. But, you know, a few minutes is what we got. I got great pictures from him, with him, and I've got a whole slew in a book that has probably 5 or 6 different pictures.
And more broadly, Lee, the development of Obamacare, was that relevant at all for what you were trying to achieve with P4?
Not directly. I mean, Obamacare is a way of paying for health care. It had nothing to do with improving the quality of health care. So it was at the other end. But it's something I feel strongly is desperately lacking in American healthcare. That is a healthcare that is accessible to everybody. And even Obamacare today is really limited in what it can do and how it does it.
Do you see it as a necessary step forward, or in order to achieve nationwide your vision, do we need a totally new system? We need to start from scratch. That's something that replaces Obamacare.
You could never, ever bring my vision by starting from scratch and building over. You have to fuse on to what's there and convince people to adapt and change. That's kind of a given one of the biggest challenges of participatory is, there are a lot of people that make money with the current system, and why change it if they're doing well? So you have to persuade them, A, that you'll improve enormously the quality of healthcare, and B, you'll cut by orders of magnitude the cost of healthcare. And that has to be done because at the rate it's escalating now, we'll be out of business in 50 years.
Yeah.
It'll take the entire budget of the U.S. to pay for healthcare.
We talked about some of its missteps, but we haven't really talked about the creation of AirAvail and the role that Nathan Price played in this.
Well, Nathan, when he came in 2011, I think it was first of all, Nathan had been a postdoc with me for 2 years, so we knew one another very well. And I switched him from his classic bioengineering mode of the analysis of metabolism to a much broader healthcare spectrum. He went to Illinois for 4 years after the postdoc. He developed a terrific group there, but he was frustrated because it didn't have a medical school. He couldn't really do healthcare. So that's the hook we used to bring him back. I will say an important part of bringing him back is every year at a ranch I have in Montana, we have, with my lab, a scientific retreat. And every year we pick a big new topic to talk about. And these retreats is one of the things everyone who goes through the lab always remembers. And I invited Nathan to every single retreat for the 4 years he was in Illinois, and he came. So we kept connected, and he saw what Luxembourg and the 100 million there was making possible, and really got excited about the possibilities. So it's when he came that we started thinking seriously in 2013 and 14 about setting up a pilot program for wellness where we took 100 of our friends and used genome-phenome analyses for roughly a year to see how it worked. And we did that, and it was possible to demonstrate enormous efficiency and effectiveness. And that was the forerunner then to creating a company called AirAvail that brought scientific wellness to consumers and so forth. And Nathan was a central figure in creating that company as well. So he and I partnered all the way on this whole vision of scientific wellness and prevention.
Lee, in 2016, when ISB made the decision to affiliate with Providence Health, had you known Red Hochman previously, and was there something attractive about that connection that made this viable in your mind?
I hadn't really known Rod Hochman directly, but I had the secretary he had for 5 years at Providence, and she told me a lot about him and what kind of person he was. And it was clear, at least among healthcare CEOs, he was a real visionary. But anyway, the chair of ISB board, Dave Saby, was good friends with Rod, and he argued to Rod that it would be a really great thing if he made me chief science officer and affiliated with ISB so they could learn systems biology and scientific wellness and things like that. So Rod came to me with those as pitches, and I instantaneously, saw it was an opportunity to really develop this million-person program, which I've been thinking about expanding it beyond what we could do with Airavail. And two, even though Airavail was going at that time up until the beginning of 19, and two, it was clear Providence would be willing to put resources into ISB's endowment, and that could give us some more financial flexibility. So those two features were very, very attractive.
In 2018, when it was announced that James Heath would succeed you as president of ISB, first, tell me about your collaboration with Jim, and has that been restorative to some degree, given that this has Caltech roots?
Well, I knew Caltech. I knew Jim at Caltech. In fact, I knew Jim when he was at UCLA. And he and Mike Phelps and I formed kind of a trio of a very advanced scientists thinking about healthcare and medicine in new and different ways. We had a science paper, I think, in 2003 or 4 that we wrote together on P3 medicine. I think we called it then. And Jim was an unusual chemist, an engineer, and physicist who had a real interest in biology and the ability to move into biology and take it on in a very deep, powerful sense, developing on the one hand technologies and on the other hand doing the biology himself. So we interacted on those dimensions. When I started Luxembourg, I persuaded Jim to be one of the network scientists for Luxembourg, and he got a reasonable amount of funding, and he invented a new technology for capture agents for diagnostics and so forth that we actually ended up making into a company and everything. And whenever I'd go down to Caltech to visit my daughter, I'd stop by and see him and stay with him. And we had a good friendship. And, in debating about who should take over when I stepped down, Jim was one of 4 people that I thought was a natural candidate. And I think he was probably the best candidate of the 4 that I selected. So we made the pitch to him. And I think what convinced Jim to leave Caltech was the affiliation with Providence, because he too was very interested in immunology and immunotherapy and getting into clinical trials and things like that. So it was a natural for him to come and step in my shoes and lead the relationship then with Providence at that stage.
And how would you characterize Jim's approach to science? Was it complementary to yours, would you say?
Well, I would say Jim was a master at small science and going very deeply into small problems. And I'm a master at bigger science and thinking more broadly. And I would argue, as I always have, the two are enormously complementary to one another. And the big broad view opens up a myriad of possibilities for small science to execute. And Jim has done a terrific job, for example, with COVID, and developing new kinds of clinical trials and exploring and understanding whole new dimensions of COVID that people hadn't known about before. So I think it's worked very well. Now, I will say, in all honesty, Jim really wanted me to build Phenome Health within ISB, but in the end, I decided not to for two reasons. One is governance. That is, every decision would have to go through the ISB board and the Providence board, and that's a nightmare. And number two, the overhead for ISB now is 88%, and it doubled the cost of all the things we do with Phenome Health. And as I have for a number of other programs I initiated, in the early stages, I ended up paying for it myself to get it started. And I just couldn't afford to pay close to 100% overhead on the science we'd start doing in Phenome Health. And I think Jim was enormously disappointed and argued that that was not healthy for ISB. But on the other hand, I have 4 ISB faculty collaborating with me, and I'm paying them to do it. So I think it's going to work out fine. But Jim he wanted to keep everything in ISB. And you know, what I learned very early on in paradigm changes is you can never effectively move a new paradigm change forward in an old organization. Mm-hmm. You have to set a new organization up to do it.
Yeah.
And it's true here, just like it was true with the other 6 paradigm changes I talked about before.
Lee, as we get closer to the 25th anniversary from the origins of ISB, some overall questions in historical perspective. So since its inception, because systems biology has its sights on all of wellness, right? Not just a particular aspect, where have you seen the most successful health outcomes when applying a systems biology approach to a particular health malady? In other words, from here, 2022, how do outcomes compare, say, between cancer and neurodegenerative diseases, for example?
Well, let me say first that one of the things about ISB is all 3 co-founders basically started each their own independent entity in systems biology. Rudy Abersol went to the ETH in Zurich and started a systems biology unit that really was very effective. Alan Adzerum started one at an infectious disease institute actually across the street from where I am now. And in fact, if you look around the world, way more than 100 institutions have the name Systems Biology Department, Institute, or Center, okay? So that question is really difficult to answer in the sense there are systems approach to, well, not so much to wellness. It's almost all the systems approaches are to disease, but they're in a whole host of different ways really pioneering effective new approaches and extending systems biology way beyond what we've ever imagined in the past. And I mean, if I had to pick out a couple of outstanding places, my graduate student, Trey Eidegger, went to UCSD as a faculty member in bioengineering. And I think he's at the leading edge of developing new integrative techniques for systems biology that have to do with health and in particular have to do with disease. I would say the Weizmann Institute has pioneered some incredible systems approaches to the gut microbiome and diet and how you deal more effectively with diabetes and things like this. So what I would say is there are just a myriad of possibilities that are exploding out all over. Most people still don't do a very sophisticated systems biology, but even at a low level, it makes a difference and you can do interesting and exciting things.
And more specifically, Lee, how do you compare the success of the systems biology approach when it comes to both diagnostics and creating and delivering new classes of drugs?
I think they're part and parcel of the same thing. I think systems biology, to simplify it somewhat, is all about defining the biological networks that mediate certain processes, wellness, aging, disease. And in doing so, as you come to understand those networks, you can identify key points where choices and decisions are made. And there you can identify biomarkers that are key for prediction, prognosis, et cetera, et cetera. While at the same time, you can show the interconnected, early especially, disease-perturbed networks before they become too complex. And you can think about rational and logical ways from blocking these perturbed networks and so forth. So I think you get both at the same time as you come to understand the origins of wellness, disease, or transitions. And the key is to go to the transitions because that's where we want to deal with disease in the future. You deal with disease before it ever becomes a manifest disease.
Lee, where do you place nanotechnology in the overall vision of ISB, and in what ways has that changed over the decades?
Well, nanotechnology is just a very powerful technique that allows you to miniaturize, to parallelize, and bring down the cost of assays and purification and things like that. So Jim is a real pioneer in using those technologies, for example, as is one other faculty member, Sui Wong at ISB. So I think nanotechnology, in its ability to miniaturize things, will in time lead us to a device that all of us will have at home that will do all the measurements we need to optimize wellness and avoid disease.
Lee, what about microfluidics? Were there specific technological advances that made this relevant for systems biology, or is it more a mature field and you saw novel opportunities?
No, it's exactly the same as nanotechnology, only at a larger dimension. Mm-hmm. And what it enabled us to do is you could put switches and mixing pots and all sorts of things in microfluidics, and we'll be able to do that with nanotechnology in time. So it was, a few orders of magnitude bigger than what you could do with nanotechnology, but it had all the same benefits.
What do you see as some of the ways that ISB has conceptualized chemistry in novel ways to realize the goals of systems biology?
Well, for example, we developed a color coding approach to be able to analyze single molecules of RNA. And so, for example, we could, with a barcode of about 4 different colors, generate 800 different tags for 800 different messenger RNAs. And that chemistry led to a company called NanoString, which has been enormously successful here in Seattle at being able not only to analyze nucleic acids in the test tube, but nucleic acids in tissue slices and so forth. So it absolutely pioneered the application of anatomical analyses of complexity. Okay.
Lee, I'm not sure if you're following. It's still very young as a field, but there is a lot of excitement about the potential of quantum computers to revolutionize chemistry and synthesis and new drugs. Are you following these developments? Do you see a place for quantum computers in a systems biology approach?
Oh, absolutely, because what we want to be able to do is integrate and look at the combinatorics of integration of millions of different features. And if you want to be able to do that, today's computing doesn't touch it. And it's going to take something like quantum computing. What I am convinced is quantum computing in those grand applications is a good 10 years off, but it is going to be transformational when it comes about. And maybe this is one of those examples where my conservative estimates hopefully will be way off, because the second we can do combinatorial quantum computing with large numbers of features, we'll be using it.
Lee, as you've indicated, the vision, the emphasis to put more work in the proactive realm, wellness upstream, and less on reactive approaches to sickness and disease. Obviously, there are tremendous cultural and economic and political barriers. Where are you most optimistic that your approach is making headway, that this is the direction that we're actually going in?
If we succeed in getting even partial funding for Beyond the Human Genome Project, and I'm sure we can do that with our partners, I think we will have a whole series of demonstration projects that unequivocally show the power of this different approach. And they initially will focus, perhaps more than I'd like to, on disease, but as a part of what I want to do with Beyond the Human Genome, I do want to set up Airveil 2.0, make all the corrections we need to have it be really effective, and then persuade a number of our industrial partners to use this in the context of their employees and get them engaged in doing so. And I think if we can have the Googles and Microsoft and Regeneron and LabCorp of the world engage in this kind of endeavor, then I think we can push wellness along right in parallel with the precision medicine will do for diseases.
Lee, if we can take a particular example, perhaps looking at your work on prostate cancer in the 1990s, how has ISB's emphasis on taking a genetic approach led both to better data analysis and better health outcomes?
Well, I would say taking a genetic approach to disease is a very complicated endeavor. And that's because one approach you can take is to look at diseases where a dominant gene causes the disease. And that's pretty straightforward. Huntington's disease is a good example. And the penetrance is 100%. If you have that gene, you're going to get the disease, period. There are other diseases where the penetrance of dominant genes is less effective, so you never can be sure quite whether you'll get the disease or not. But if you have it, you better follow it closely and try and do something. At the other end of the spectrum, there are genetic analyses that have been done on hundreds of thousands of patients for particular diseases. And these are called polygenic risk scores. And what these demonstrate is 10s to up to 100 genes that each have a very small role in causing a fraction of the disease. So and if you have the complete genome sequence, you can convert those scores into genetic risks. And we've done that for 54 of these diseases. And what we've demonstrated, if we put the Airvale people in 5 different risk categories from very low to very high and in between, is that you have to treat very low risk very different from very high risk individuals. For example, for increasing LDL cholesterol, which is a proxy for heart disease, we've shown if you have a high genetic risk for LDL cholesterol and you have high cholesterol, the only thing that'll bring it down are statins or chemicals like that. Whereas if you have low risk and high cholesterol, diet, exercise, all of those things bring it down beautifully. So the point is, we want to know all the polygenic scores so we can treat people at either end of the spectrum better. And we certainly want to follow closely people at high risk to get the earliest transitions to start reversals. So genetics is, for most common diseases, is going to turn out to be incredibly complicated with lots of genes involved. And different people will have different combinations of the genes, the gene variants.
Lee, as you continue to push for your vision beyond the human genome, in what ways does just the phrasing beyond the human genome suggest that the original Human Genome Project is complete? And in what ways does it simply suggest that you're pursuing questions beyond the scope of the original project?
It's the latter completely. I mean, what the original Genome Project did was to get a prototype sequence for the human genome, and they were successful. And that's the prototype for all the genome sequencing, complete genome sequencing we do now. But beyond the human genome brings in not only the genomics, that's important, but it brings in the phenomics, which are blood analytes and gut microbiome and digital health and all of those things. And those are important because there have been a number of classic papers looking at the contribution, the elements of disease propensity. So the genome causes 30%, the phenome causes 65%, and the current healthcare system and its inadequacies cause of the order of 5% of the diseases we run into for various reasons. So you can see the phenome is beyond the genome. They did none of that at the first one. But it essentially, the phenome looks at your genome, at your lifestyle, and at your environment, and it integrates those together to give you, at an instant in time, measurements of how healthy or how diseased you are. So the phenomes let us follow people throughout their lives, assessing those three contributions: genetics, lifestyle, and environment.
And in your vision for beyond the human genome, is it so all-encompassing that at a certain point it will actually influence the way patients and healthcare practitioners interact at that level?
Oh, absolutely. Yeah.
What does that look like?
For example, one of the things that really made Airvale successful, and by that I mean persuaded their customers to carry out the actionable possibilities the data gave them, unique for each customer, were coaches, okay? Now, a good coach can probably handle 100 plus individuals, so coaches don't scale. And the coaches were trained in psychology and often in nutrition and even nursing. So they were a key element. So what I think is going to happen in the future, and we're talking with several companies on this, is you'll have a personal avatar that'll be your coach, that will take all the data you get from your home device, and it will give you a rundown on what you should be doing, and it will nag you to do it. So those are the kind of things we're thinking about. I mean, healthcare in the future is going to be done at home. It isn't going to be done in big capital-intensive hospitals, which are focused now entirely on disease, right? We don't need those. We won't need those. So it's all going to be done at home. Most of the measurements are going to be done with simple digital devices, very inexpensive, microfluidics, nanotechnology, quantum computing. All of these things are going to transform what we can do in terms of instantaneous readings that are continually assessing and optimizing your health trajectory.
Lee, nowadays undergraduates at Caltech, in large part as a result of your legacy, they can now pursue biological interests across the institute, whether they're math majors, engineers, chemists. That's the idea. For ISB, for systems biology, is the multidisciplinary approach that students are now embracing, are you already seeing that as a strategic asset for what you're hoping to accomplish long term?
Right. And there is a discipline called bioengineering that began to do that 30 years ago or more. So, but now it's gotten more comprehensive and broader as we've brought in more and more sophisticated technologies and computational tools.
I wonder if you can talk a little bit about why open access, open source research is so important for what ISB represents.
Well, what was very interesting about the 5,000 data clouds we generated for Airvale is now 3 years after Airvale closed, we've just barely scratched the surface of all the analyses that can be done. So, and for Beyond the Human Genome Project, all of those data are going to be available to anybody who wants them, and we'll encourage anyone who's interested in them to ask whatever questions they want to do it. And good students are going to continually come up with unusual, provocative, interesting approaches to the data. And you want to get that data out to as large an analytic audience as you possibly can if you're going to maximize the benefits to society.
Lee, how did the idea of blood protein fingerprints come about, and why is this approach so important to systems medicine?
Well, when I was thinking back in the early 70s about the analogy of the elephant, you remember, and the six blind men, and what was clear from that analogy, if you thought about healthcare at that time, is in that analogy, each doctor, quote, only looked at one feature and defined the organism based on that one feature. But the other thing is, all of the features were on the outside. And frankly, at that time for physicians, a lot of that was true. So in thinking about how would you possibly make measurements about the inside of an elephant or of a human, I got the idea that it bathes all of the organs of the human, and clearly molecules are sent from organs to the blood. And clearly, if we could learn to read those molecules, they would give us reflections of the state of their cognate organ where they originated. And that was a simple beginning of blood as a window into health and disease that I pushed. And then later we developed all the tools to be able to do it.
And where do you see this technology going from here?
Well, it's just getting better and better. I mean, Illumina just bought a company that was able to demonstrate that you could look at epigenetic marks on DNA from blood cells, and you could identify from those about 50 different cancers. And, that's an extreme example of diagnostics and what it can do. But we're going to see that again and again and again.
Lee, what's the current state of the Accelerator project? And are there successful ventures from it that you feel are already contributing to ISP's long-term financial viability?
The Accelerator has evolved away from ISB as I stepped away and they stepped in other directions. They have generated companies that have been very successful, so the idea was a great one. But I just didn't have the time to put in to keep up all the effort and energy required to keep it in the ISB axis. And, I talked to Jim Heath about it, and he had the same feeling that those things take a lot of time if you really keep connected with them. And so it was a great idea, and it succeeded. And in fact, it's metastasized to New York City now. So there's an Accelerator in New York City and one of their big biotech centers. So that idea is a key one. What I am going to do with Beyond the Human Genome Project is have side by side something I call an accelerator incubator, which will be Phenome Ventures. And we will spin off the intellectual property we generate from the data into Phenome Ventures, and it will create either companies that emerge from it, those opportunities, and we think there'll be companies emerging from each of the major chronic diseases that we analyze. So diabetes, cardiovascular, Alzheimer's, and other degenerative neurologic diseases, cancer, etc. One or more companies. And so I'm going to have another accelerator, and we'll see how that goes. Only the idea here will be to retain the profits to keep Phenome Health running beyond the 10 years of the federal support we hope to get.
Lee, I wonder if you can reflect on the import of your collaboration with Eric Davidson over the years and what that meant for what you've been trying to achieve.
I think Eric Davidson is one of the greatest scientists I've known. And I think if he lived a little longer, he absolutely would have gotten the Nobel Prize in developmental biology. My collaboration with Eric was enormously fun. We were good friends and shared a lot of things together, food and drink and things like that. But I taught him a lot about technology. He taught me a lot about developmental biology. And it was one of the great friendships of my career. I think his dying suddenly was the hardest loss I've had in terms of a really good friend that meant a lot, both scientifically and personally to me. I mean, we came together in 1970 to Caltech as the first young assistant professors they'd had for ages. And we were both fiercely independent and knew where we wanted to go and what we wanted to do. And it was just a partnership that evolved from day one up until Eric died.
What was Eric's approach that you respected so deeply?
Eric was able to do very deep, small science on a global scale. So what he did was he developed completely the developmental map for the sea urchin for the first 30 days or so of its development. And he did the complete wiring map of this development. He validated virtually every single thing, every single hypothesis that was a part of that map. And it was just a tour de force. I mean, no one in developmental biology has come close to what Eric Davidson did.
Lee, moving closer to the present, the creation of the mRNA COVID vaccines, obviously this is going to go down in history as one of the great scientific triumphs. Do you see systems biology as playing a role, either from the basic science for how we understand mRNA, or the speed simply with which we were able to deploy the vaccines? Do you see ISB as part of this legacy?
Well, I see systems thinking and systems approaches as a part of the legacy. You know, ISB does not any longer own systems biology. It has spread to the world, and I would guess there are a lot of systems biology students that have never, ever heard of the ISB or anything like that. And that's the best thing that can happen in science. And frankly, that's one of the reasons I wanted to move on and do the next big thing that's really new and different. And that's going to be this Beyond the Human Genome Project.
And that's in a way part of the grand plan, that you have set forth these ideas and they take root throughout the world, and whether or not people have that appreciation, that's really a secondary concern to you.
Yeah. You know, one of the things that was interesting is when I was getting ready to start ISB, I had a really good friend in the National Academy at MIT who said, you know, Lee, this systems biology is all hype. It's never going to amount to a single thing. He said, why are you wasting your time? You can do really good and creative things. And I said, well, we differ on that completely. But what was interesting is the National Academies did a book later, 10 years later, where he was co-chair of the committee that wrote it on the future of biology. And they described perfectly, without using the word, but perfectly, systems biology as the future of biology. So I've always thought that was an enormous accomplishment on his part to go from absolutely convinced it was hype to this is the future.
Well, Lee, now that we've worked right up to the present, for the last part of our talk, some overall questions that I'll ask you to look back at your career, and then we'll end with your sense of where things are headed. So first, when you look at Caltech now, just for example, that we have a division BBE where biological engineering is really right there. So of course the irony is that had you stayed at Caltech, perhaps you'd think that this would be a perfect place for you to have spent your career. So I'll ask you.
Well, and I, more than that, tried to persuade biology that I could set up that department.
Right.
Failed. Yeah.
So in the way that obviously you were ahead of your time, looking at what Caltech has done since you've left, what is both frustrating about that and also gratifying about where Caltech has gone?
Well, look, I think the major thing you can say is Caltech biology has thoroughly embraced this cross-disciplinary approach to science. In the biology department they have now, and they've got wonderful people they've hired doing really interesting things. And I would say it really has embraced systems biology as well. I mean, where I would be a little disappointed is I don't think it's very interested in medicine yet, or at least they haven't hired people that had that interest, but that's a matter of taste. So I'd say Caltech biology is in a pretty good place.
Do you think that a strategic partnership with a hospital is in Caltech's long-term interest?
It would be if you had a leader who knew what they were doing and chose the right hospital partnership. Huntington might not be the right partnership. I can't say these days, but I think you go with where really good people are. And if you're going to start something new like that, you better have someone who has an idea that can grow in the Caltech environment.
Lee, in all of your adventures in business, what have you learned about when to entrust financial decisions to people with MBAs or an economic background? And when do you understand that the scientists really need to be making these budgetary decisions?
Well, I think in the initial phases of any company, the scientists play a critical role in the budgets because most companies are all about discovery, okay? Now, as they become successful, the scientists don't want to and don't have the time to continue with that. And you bring in the professionals that do those kind of things. And so, you want to always have leaders in finance who respect the science and appreciate it and make sure it is appropriately rewarded. So the key thing becomes the leadership in finance to make sure you have the right thrusts and directions and things like that. But, the leadership in science and the leadership in the company growth can fight with one another on occasion over resources and how the resources should be used to optimize one or both. So it's not a trivial equation.
And Lee, because you have so much experience in all three realms, going forward, what is the optimal mix for systems biology in terms of garnering support from the federal government, from industry, and from philanthropy?
So I think the most constrained of those three is the federal government. And I always think you should get as much as you can from the federal government because in some ways, at least with regard to industry, that has a lot less attachments and constraints, okay? Philanthropy is absolutely ideal, but you have to be able to map that into your philanthropic individuals' interests and passions and love. And that's not a trivial thing to do. And it takes lots and lots of time to do it. And that's why we have professional fundraisers. But I think where it is important that the scientists really keep their touch in is in philanthropy. Because I've seen fundraisers really mess up, and I've experienced that. Big asks in horribly inappropriate ways where I assumed they had the sophistication and the background to be able to, deal with an individual without me. And so, I mean, for philanthropy, it's all about doing something that's, going to set a new mark, a new phase, open up new possibilities, create a new cure for cancer. I mean, those kind of things. So, and the people that can be the most convincing are the people who really understand what it's about.
Lee, how do you compare when you look back at all of your achievements, both in building institutions, furthering basic science, helping patients at a fundamental level? How do you compare those different satisfactions?
Well, they're really very different satisfactions. I mean, there's nothing like the joy of discovering a new concept that no one knew before. In molecular immunology and cancer biology, I've had that experience a number of times. And there's nothing more exciting than developing the first automated DNA sequencer. I mean, and having a little understanding of what it was going to do, by no means realizing how transforming that technology would be. I think in terms of institution creation, they're always born in enormous controversy and with enormous skepticism. And you don't appreciate them until later after they've succeeded. And you could say to everybody, see, it worked. And so in a sense, that's a very different kind of retrospective appreciation of kind of things. But certainly in changing fields in major ways, whether with tools or visions about things, that too is very exciting. And, I'm just finishing up the final editing on the book I wrote with Nathan Price on what should be the future of 21st century medicine. And, that's such a satisfying thing to have done and struggled through and laid out how we're going to do it, what we need to do, and, made the arguments that hopefully are going to at least penetrate into some subset of the consciousness of healthcare leaders and physicians and especially patients. So we'll see how it does.
Lee, if you ever have the opportunity to provide advice or be a mentor to undergraduates, when you look at your own experience and deciding to go for the medical degree, even if your aspirations were in a research environment, would you say that that's still a good path for students nowadays?
Absolutely, because it gives you a deep understanding of medicine you'll never get. A deep and broad understanding you'll never get from just reading about one specific disease yourself. So no, I think getting the MD in 3 years was absolutely spectacular for me. And I would recommend it for anybody who had interests that bordered on health and wellness and disease and things like that.
Lee, in a world where the P4 approach is fully embraced, obviously this could and should have implications for our notions of normal lifespan and human longevity. If you could use your imagination, what might a normal lifespan look like at some point in the future when these things are embraced?
Well, what I would say is we'll be able to bring lifespan, how long you live, into complete coordination with health span, how long you live healthily. So I really envision with what we're talking about now, bringing the majority of individuals, even people like you and me, into their 90s, mentally alert, physically capable, and giving them an extra 10 to 20 years of a life that's possibly productive. And see, a big question is, if we let you live a lot longer, are you going to use it effectively? And what does use it effectively mean to you? I mean, frankly, maybe some people would just like to play golf the whole time. I think that would be an enormous waste, but that's me. I don't play golf. So, but I mean, but the sociologic question of if you live into your 90s, and I think it could well be beyond even that, mentally alert, physically capable, how are you going to support yourself? Have you thought about retirement? If you retired when you were 65, my feeling is, if you're really healthy, why retire? And if you're bored with what you're doing, go do something else. This one of the pieces of advice I always give students is, the two key ones are, look, be very cross-disciplinary systems in your thinking, and every 10 to 15 years change in a major way your career, because it'll make you insecure and uncertain. You'll learn a lot. You'll get all excited again about things, and you'll renew yourself. So your bell-shaped curve for success won't look like that, but it'll flip each time you change your career. You'll just keep going up. So that's a really attractive kind of idea.
And Lee, for you, obviously, showing no signs of slowing down, going as strong as ever, besides the personal satisfaction that you feel in remaining as active as you are, is it also important to convey that you practice what you preach, that other people see what you're doing and what you're capable of?
Well, I have a slide that shows all the things I learned from our endeavor into scientific wellness and how I've changed various aspects of my behavior. So I do show them that I practice what I preach.
Lee, I know one of your favorite quotes comes from Freeman Dyson. New directions in science are launched by new tools much more often than new concepts. Now, Freeman, of course, was a physicist, and yet this resonates with you. So I wonder if you can talk a little bit about how it gets to a deeper truth where the distinctions that we draw between physics and biology are perhaps not the right approach. They're not the right way to look at these things.
Well, the really key thing for a new tool is basically it lets you look at the world in a new way. And you see things people have never seen before, and they all demand to be explained, right? In a new concept, you've got the same data, you're chugging around trying to think of, it's just a variation on a theme. But a new tool, and I would say a spectacular new tool, has been large-scale DNA sequencing. It let us look at the genome. It just revolutionized, and our understanding of the genome is still right at the very beginning, but what we've learned is just staggering. What we're going to learn in the near future is even more staggering. Just a sec. Let me answer this. Hi, what's up? Oh, that's fine. fine. I'm still on an interview that will go on for a while yet. So, yeah, just let me know either way. Maybe what I'll do is go next door and have some sushi or something if I need to. But let's see. So, when do you think you would come home at the earliest? Gee, this is a terrible time for traffic, I would guess. Yeah. Okay, whatever you figure out is fine. Cheers. Bye-bye. Okay.
So Lee, going back to Freeman Dyson, obviously for physics, we can talk about a quantitative approach. For you, at the end of the day, is biology fundamentally a quantitative discipline?
I think biology is fundamentally becoming a quantitative discipline. Yeah. And for example, things like imaging, with the new imaging analytic techniques, you can determine area and depth and shape and all sorts of kinds of things. If you measure blood analytes, that's all quantitative. If you measure the gut microbiome, all of the important digital health it's all, whether it's brain digital health or Fitbit body digital health, it's all quantized. So what systems biology is moving us toward a realization of is that all of biology behaves in quantized units. So, for example, the most fundamental unit is the basic, the amino acids of proteins, the nucleic acids of chromosomes, the metabolites of metabolism, and so forth. So you go from those molecules up to a cell. That's a unit of organization in which things operate discretely. And you can go from there to an organ. That's collections of cells that do complicated kind of things. And you can go from there to the whole organism. It integrates. So it integrates these different levels of information seamlessly. And that's, in a sense, what we tend to do when we break them down into their quantized units, to carry out integrations that give us insights into the hierarchy of the organization of biology and what's happening.
And maybe,
yeah, I think, in a sense, biology is both digital and analog in some senses, because, for example, concentrations of molecules in the blood make a difference, and that's more of an analog kind of measurement than it is measuring the number of molecules per unit blood or whatever. So
maybe the question will border on the philosophical side, but your answer emphasizes biology as a discipline, as our interface, as our approach. Is that to say also that life itself can be reduced to numbers? Is that ultimately what this means?
Well, it depends on what you mean by reduced to numbers, because life has some core fundamental units that definitely have to pre-exist if you're going to replicate life and so forth. So can you reduce guanidine to a number? I guess you can argue that different ways. I don't know. It's not a simple reduction anyway.
Stemming from that, are there some mysteries in biology that no matter how many advances we make, you're comfortable classifying as simply unknowable to the human mind?
I think the only one I would categorize as possibly in that category is consciousness. And, maybe that's just being able to deal with 10 to the 15th neurons and their connections and their associations. And it seems that consciousness will be the last problem in biology that gets solved. I'll put it that way.
But you don't think that there is a potential spiritual dimension that would serve as a block point to fully understanding consciousness?
I would remain agnostic about that. I have a friend of mine that's that has AML, acute myelogenous leukemia, and that means you can live maybe a year and a half, and he's toward the end of that living. And I've talked to him once a week most of that time. And what has been very interesting is how he's come to accept the inevitable and find peace with it in a kind of religion that is Buddhist, Confucius, and like, and it's brought him enormous peace, and it's allowed his family to live with this horrible disease almost happily because he's so positive and helpful and everything like that. So, I never thought about spirits and all of those things in any very deep way. I didn't have much to say about it. I haven't been religious, but kind of the peace that emanates from him is enormously attractive and compelling if you ever have to go through that yourself. So you can wonder, is that just another aspect of consciousness? I can't answer that.
Lee, for you, obviously, there's no viable notion of retirement, but for however long you want to remain active, is there a prioritization for you of all of the things that you're involved in? Is there a prioritization of the things that are most important that will serve as a guidepost for the next N number of years as you chart your future?
I want to accomplish the revolution in medicine that comes from being able to say, for each individual, we can assess and optimize your across your life trajectory, your body and brain health. That's it. I mean, that's and look, it's going to take another 12 years. It'll take a year or two to get federal money, and it'll take a while to do. So I've got a lot to do. I can see stepping back and letting younger people play leading roles in this effort. But right now, there isn't anyone that could begin to do that with the experiences I've had and so forth. But I have a couple of young people who are really good, and I'm going to expose them to everything and try and bring them up to snuff as soon as possible. And it would be nice if I could be philosophic and not have to organize kind of everything as I am right now. And that's incorrect, because I've got really good people working for me, but they still need their daily lists of these are the things we should get done today kind of thing. But they'll grow and mature.
Well, Lee, for my last question, looking to the future, you're so deeply respected as a visionary in so many fields. I'll ask you to be a real visionary now. I know that you can look out 10, 20 years in the future to see where things are headed, but at that point, there will be questions and opportunities as a result of these advances that can't even occur to us now. So using your imagination 20, 30, 50 years into the future, what are going to be some of the most exciting opportunities and advances in biology and human health as the things you're advocating now come to fruition?
Well, I'll answer the question, but I'll give it with a caution. I was asked in, God, I think it was 1990 by a pharmaceutical company to come and give them a lecture on what I saw 50 years in the future. Okay. So I went back 50 years from that and discovered that that proteins were thought to be the genetic material from which life was constructed. And the only point I made is extrapolating 50 years into the future. What happens if we discover the equivalent of DNA, and then everything I'm saying is in a sense irrelevant, right? And I think that's the same with 50 years. But look, there are things that you can say. I think if I succeed in what I'm planning to do, I think we'll completely control chronic disease. I think number two, I think we'll be able to live healthy, productive, fruitful lives well beyond 120 or more, okay? And maybe significantly more. I don't know. I think we haven't talked about aging and the fact that solving the problem of aging is going to be infinitely easier than solving the problem of cancer, because there are straightforward ways you can go about it now. Don't want to get into all that detail, but that's an area I'm really interested in. And if we really succeeded, it could be substantially more. But then you get into these psychological questions of, do you want to live that long? I mean, and so it comes to a question of, can we educate people so they continually reinvent themselves and reinvent their enthusiasm? That's what we're going to have to do if we give them the ability to live that long. I would say a fourth thing, I think we're going to be able to easily replace any part in a human you want to replace, possibly but the brain.
Right.
I just don't know about that. But I bet you can replace real parts of the brain and everything too. If you had, for example, a stroke, I bet you could repair that. I think we're going to be able to design humans to go to other worlds and tolerate temperatures and compositions and food that were unthinkable now. Will we be able to move things well beyond the speed of light, or even at the speed of light? Gosh, that's not something I'm really qualified to talk about. I would imagine we can get pretty close. I think we'll automate and make effortless many of the things we need to keep our body and our brains optimally operating for very long lengths of life. Okay. I think we'll have ativars that can be our personal health coaches, that will be our mothers, that love us and tell us, look, you've not done X. It's time to do X. It's been on your list for 3 weeks now. So, I mean, we're going to invent, and they're being invented now. Trey Eidegger, one of my former students, is inventing new ways of integrating together different aspects of complexity that are really striking, and just had a recent paper in Science on this this whole approach. I think we'll absolutely be able to deal with mental illness and addictions and the like there. And I think we'll be able to probably deal with most neurologic diseases one way or another. I think a lot of the worst neurologic diseases and degenerative diseases are really lifestyle environment much more than they are genetics, frankly. So, well, is that a long enough list of things?
I would say also, Lee, if I can just observe, underscoring all of this, for you is obviously a fundamental optimism about the human condition, that our lives are precious and that they're worth caring for, and we can be productive and healthy in ways that simply are not conceivable to us now.
Yep, that's absolutely true. And I think, again, that's the importance of education, making people realize the importance of new learning, of reinventing yourself, of interactions with people and colleagues to do important things, et cetera, et cetera.
Lee, this has been a phenomenal experience spending all this time with you. It's a tremendous resource for the history of science and a true point of pride for Caltech. I'd like to thank you so much for doing this.
Sure, my pleasure. So